Okay, so we are at 9:01 Eastern Time. Just a quick word. So I'm Mike Hewitt. I'm not on video, but you can maybe see my face. I'm the president of TSL this year. To try and keep us all engaged in each other's research, we're doing a virtual seminar series. I'm very pleased and happy that Dr. Van Hentenryck agreed to give our first session. Just one quick note, we'll be having these on a monthly basis. You may have seen a previous note that I sent out via Connect regarding our subsequent seminars, but you'll also get lots of messages about them going forward. But you didn't come here or attend, I should say, to hear me speak, so I'd like to turn it over to Dr. Van Hentenryck. And Pascal, thank you very much for doing this for us.
So thank you very much, Mike. It's a real pleasure and honor to give this first virtual TSL seminar. And I'm going to talk about on-demand multimodal transit systems. And in particular, one of the things that I will try to do is to talk about some recent work in which we have been trying to assess the resilience of this system and also capturing the mode choices of people. But I'll give you an overall introduction to on-demand multimodal transit systems before. So this is the outline of the talk. I'm going to start with some background and motivation, why we are doing this. And then I'm going to give you an overview of the on-demand multimodal public transit systems. I'll talk a little bit about how they are planned and operate. And then I'll talk about resilience, how resilient they can be in a pandemic, for instance, and how we can actually capture the mode choice that users can take when they decide whether to use transit or their own vehicles. And then I'll conclude. This is work with a huge amount of people. So it started in NICTA in Australia about seven or 8 years ago with Phil Kilby and Arthur Maheo. It continued at the University of Michigan, and you see some of the names who contributed at that point, and some of them are still collaborating with us. But most of the work that I will present today has been happening in the social mobility group, socially aware mobility group at Georgia Tech. And you see some of the people there. I'm going to credit some of them during the talk as well, obviously. We work with a lot of transit agencies, and we are very grateful to them because they give us a lot of data and a lot of insight. They know how to run these systems, and we learn a lot by interacting with them. So you'll see various case studies today. So let me start with the background and motivation. Why do we do this? And the key reason why we are doing this is we want to actually mobilize accessibility. We want to make transportation much easier for many segments of the population. Why? Because it's extremely important for getting a job, for instance. In the US, the best predictor of a poor social mobility is still car ownership. And so if you have a car, you're in a much better position than if you don't have one. It's also very important for healthcare. There are millions of people in the US who have actually a health insurance, but they cannot get to the care. And therefore they miss appointments, and their health overall is much worse. Healthy food is a very hot topic these days. And once again, there are tens of millions of people in the United States who don't live within a high quality supermarket, and mostly they shop in convenience store. And you can see many of these actually supermarkets relocating to more healthy part of the various cities. So once again, if you have better transportation, you can access these supermarkets, you can get a much better nutrition. And finally, so this is And finally, education also is really important. And in some cities in the United States, some of the children have to switch buses 2 or 3 times before getting to the school of their choices. So which also means that they miss some after-school programs and so on. So what we're really trying to do is make transportation much more convenient and affordable for various population segments. Now, why is this so hard? One of the reasons is congestion. So I live in Atlanta, one of the worst, congested cities in the US. That's not what they tell you when we are recruiting, right? And people have argued that TNCs like Uber and Lyft would solve this problem. But there was a very interesting counterfactual study in San Francisco showing that Uber and Lyft have actually increased congestion by about 20 to 40%. So this is not really a solution. So what about transit? When you look at transit, it's a much better use of the infrastructure, which is obviously finite. You see the space that a bus takes compared to the cars for carrying the same number of people. Therefore, you would say, yes, that's why isn't that the options that everyone is using? And the main reason is the graph that you see on the right. So this is a graph telling you the public transit share of various cities in North America based on the distance you have to walk to get to a transit stop. And what you see is that if you make people walk a quarter of a mile, you lose essentially 90% of your ridership, except in the city of Calgary in Canada for some reasons. So you really need to have people walk less than 50 meters, and actually less if you can, if you want to keep more than 90% of your ridership. So that's the challenge, and this is called the first and the last mile problem. Now, one of the things that I want to tell you as well is that transportation is a big contributor to greenhouse gas emission. About 30% of greenhouse gas emission currently in the United States is coming from transportation. And out of that, about 60% from small vehicles. So once again, if you have a more efficient transit systems, you also have a greener environment. Now, these are the bad news, but I want to talk about the good news. So, so we have a couple of key technology enablers. And this may seem very odd, but actually this is, in my opinion, the most important one. This is the fact that we have 24/7 connectivity. You can connect to people, you can connect to the infrastructure, to vehicles. And that makes a huge difference for designing new transit system. And obviously that's what Uber and Lyft have realized. The other thing which is important, and I will talk a little bit about that later on in the talk, is autonomous vehicles. They will come at some point in different shape and forms, and they will make a very significant difference in terms of cost, as you will see later on. And finally, and not last but not least, there is also a very important component, which is going to be the optimization, the machine learning technology, which is needed for actually powering this new transit, well, this new mobility system. And I think I recommend everyone to read this paper by Niels, Mike, and Barrett, because it's actually making the case much better than I could do. They have this nice paper that just came out of Make No Little Plans, and they are essentially arguing what I'm telling you, that we have a role as a community and we have the skills to actually power these new mobility systems. And I'll come back to that paper, but I encourage everyone to read it. But I'll come back for isolating some particular quote later on. So let me. So what you can see is essentially us, taking some recommendation of that paper and implementing them. So and I'm going to talk now about on-demand multimodal transit system. So what we are trying to do is to try to do what Lyft and Uber have done for taxi services, which they have really revolutionized. We are trying to do that for the same way for transit. And this is more complicated because now we are dealing with governments and so on. But we believe that we can essentially do the same kind of transformation for public transit that what Uber and Lyft have done for taxi services. And so we designed this on-demand multimodal public transit. And I'm going to try to explain in two ways what they do. So this is the system view, and I'll show you a short video in a moment from the user view. So what is an on-demand multimodal transit system? It's a system which combines fixed routes for rail and rapid bus transit, for instance, with on-demand shuttles that pick people where they live and bring them to their destination. So it's really a multimodal system, and I will explain you why this is interesting. But let me show you a short video to show you how a user would actually use a system like this and what it would mean from a system standpoint. So a very short video, but I will show you what a user is actually doing. So now you have a little bit of an understanding of what the system do. I think one of the message of this video is to show you that everything is synchronized, right? The system is planned and operate holistically. So the shuttles are waiting for people coming from the buses or the rail, in advance, so they don't have to wait, and the apps is telling them which shuttle to board and which shuttle is waiting for them. So let me show you now a view of the system and what is happening when you look at this system globally. So this is the early work that we did in Australia. And so you see, this is the city of Canberra. You see that they use a huge number of bus stops in Canberra. Everything which is red there is a bus stop. When you see that, the height is so this is a 3D video. When the height is a little bit higher, that means that somebody is waiting for a ride. This is a hub. And therefore, this is where people are waiting for the buses. The buses are blue, and the taller they are, the more people are in there. And so look at this part here of the video on the left. You see that a shuttle is going to be actually picking up this particular person, and now is going to bring them to this hub where the bus is waiting. You saw that the shuttle actually picked up somebody else on the way. This is a ride-sharing system. Now you see this bus there. This bus is moving along. People are waiting there at the hub, and the bus is going to pick them up and move them to the next destination. So this is like how this system is organized from a system standpoint. So on-demand multimodal transit systems are on-demand. They are door-to-door. They serve the first and the last mile. But they're also multimodal because we want to deal with congestion and economy of scale. So we have typically fleets of various types of vehicles, trains, rapid buses, shuttles, even potentially scooters and bikes. We are looking into that. The system can be entirely electrified because we own the fleet. So there is no range anxiety. And you can actually show that you don't have to charge the vehicles more than once or twice a day. It's also a sustainable business model, and I will try to argue that in the rest of the talks by showing you some numbers. As I told you before, the system is planned and operated holistically, and the goal for us is to make it accessible for entire population segments. And once again, I will talk about this during the case studies. So this is the city of Canberra again. And this is the kind of results that we had for that particular transit system. So you see the new transit system and the old one, and you can see the difference in time here. It's a factor of 2. Now, Canberra is a very wide geographic area, so this is a kind of an ideal case for us. But you see a very substantial, decrease in transit times, in travel time, and also essentially a 50% reduction in budget. So which is kind of a very nice as a case study. Let me show you a completely different system. So this is the University of Michigan transit system. This is a big transit system, about 50,000 people a day, about 1.5 million a year. And a lot of the students and faculty and staff are moving across the different parts of the campuses. We have the North Campus, the Athletic Center, and the Central Campus, and also the Medical Center. And so you see that the buses are heavily used. A lot of people waiting everywhere. So we did a pilot there. So this one of the shuttles that we actually used. And this is the kind of waiting times that we were able to achieve. So we tried to design a system such that the waiting time was as short as possible. And you see here an average of about 3 minutes in this particular pilot, physical pilot there. This is the budget, and I promise you that I will talk a little bit about this. We fit inside the budget of the transit agency, so we don't exceed the budget at all. But now a very interesting thing happened. Most of the cost here is actually dedicated to drivers of the shuttle, drivers of the buses. So the day you have automated buses or you have automated cars, a very significant portion of this budget is going to decrease, and you can further improve the quality of service of the transit system. You can expand it or make it even better. Let me talk. So this was a completely different story here because it's a very small area. It's about 5 by 5 miles, but it's extremely dense. A lot of students and faculty and staff are moving. So 2 extreme cases. What I want to talk about now is Atlanta, which is a very interesting case study because it's a very large city. It's also very dense in various areas. And so, as I told you, it's one of the most congested cities in the US. It's the 11th one. You essentially lose about 100 hours in congestion every year when you are in Atlanta. So that's about kind of 10 working days. And the total cost of congestion is about 3.5 billion, so massive. No, one of the interesting things in Atlanta is the fact that the public transit share in commuting is only 10%. So you have to compare that to Boston, which is 33%. New York City is 56%. So very small share of commuting is with transit. So it's really a car-oriented city in a sense. The commuting is about 30 minutes by car and 46 minutes by public transit. So if you have a bus. You see the design of the transit system there. This is a transit system, Marta. You saw it in the video already. The red line, the blue line, and the yellow line there are the rail. So that's the backbone of the system. And then you see all the bus line. I think there is about 450 bus lines, so massive number of bus lines. One of the interesting things when you study this transit system is that the demand, at least in Atlanta, is extremely predictable. So we have this signature for every one of the rail stations telling you how many people are boarding and alighting at those stations. And they are really, really very similar across various months and various years. So that makes it easier for us for actually designing the system. So it's very predictable in terms of the demand, the ridership. So what I'm going to show you is a design of an on-demand multimodal transit system for Atlanta. We look at the peak, morning peak, 6 to 10 a.m. because that's the most difficult one. We took the cost of the buses and the shuttle from Marta. That's the cost that they have for a bus and also their paratransit shuttles. The bus frequencies that we will have is 2 to 4 per hour. And we also limit the number of transfer. People don't like to transfer in general. And during this 6 to 10 a.m., we have about 55,000 people. The result that we have, and I'm going to show you the design in a moment, is about only 26 buses are left and about 1,100 shuttles. So you see the design of the ODMTS on the right. And there are a couple of things that I want to point out. So when you look at the rapid bus lines that we are introducing, they are essentially expanding the rail. So they are not in between weird places. They are just making the rail backbone larger because it's kind of limited inside Atlanta. And the other things that you see is that the shuttles are really acting as feeder to and from this backbone of buses and rail. They rarely serve direct trips, but it's about 5% of the overall trip. So you see really the shuttles acting as the first and the last mile feeder to the backbone of the transit system. Let me give you a comparison here. This is on the left, the current system, on the right, the new one. We massively reduce the number of buses. Obviously, we use a massive number of shuttles, and we are actually cheaper in cost compared to the existing system. But the main point is that we are able to almost reduce the transit time again by half. So we don't reduce the budget by half. This is a much more complicated and large system, but we reduce the transit time by half. One of the interesting things on this picture that you see there at bottom right is the use of ride sharing in the shuttle. And most of the time, and we'll come back to that later on, is the fact that you see that the shuttle have only one passenger. Is really during the really peak times that you see that we have some ride sharing. That's when you need the ride sharing options. Otherwise, most of the time you're alone in a shuttle, which is kind of nice. Let me show you a video. This is the transit system on the data that I've just shown you. And you can see the rail, you see the trains moving, you see the bus moving as well. And then obviously you see a lot of the shuttles, which are acting as first and the last mile. This is based on a video, on a simulations that we have. The simulation is very high fidelity. We know how many people are in every one of the rail, every one of the trains. We know also how many people are inside every one of the buses and every one of the shuttle at any one point, and we follow the real transit schedule. So this is really a very high fidelity simulation. The only thing that we are not capturing is congestion, but once again, this is not a limitation because what's going to happen, and this is already happening in cities like San Francisco, the rapid bus will probably have dedicated lanes. And the shuttle, as you can see, and I will show you in the next video, are really serving the local, are very local, and therefore they don't have as much worries about congestion. So this is a zooming on the downtown here. You see downtown there. This is close to the stadium there. And one of the things that I want you to see is look at these shuttles, basically feeding the end of this rail line. They're also feeding this station there, which is Vine City. It's one of the most popular stations there. And so you see, this is really what the shuttles are doing, feeding the rail or feeding the buses. And so this is, once again, based on the data that I've shown you before. So let me tell you a little bit how you do this, how you plan and operate this system. So the design of the system starts with the demand estimation. So where people are, starting and where do they go over time. Then you do the network design, and then you do the fleet sizing. I will go over some of this in a moment. And then when you operate, you do the trip design, as you've seen in the video. Then we do the real-time dispatching. I will go over that. And then we do the state estimation. We have to know where people are at every point in time. This is the evaluation methodologies when I'll talk about resilience. Once again, it's follow exactly what I've told you. So you estimate the demand, you do the design, you do the fleet sizing, and then you simulate. And the simulation use the real-time shuttle dispatching and routing that we are using during operations. But we use various scenarios that will change the demands or change the vehicle capacities. So let me talk a little bit about the network design, which is work that I did with Arthur and Phil Kilby. And the key point there is, to design the backbone of the system. Where do we put the rail? Where do we put the buses? What are the frequencies? And this is a very large-scale optimization problems, in a city like Atlanta. And the objective function is typically a multi-objective where we have to minimize the cost for the transit agency, but also maximize the convenience for the users, the riders. It's inspired by very traditional network design optimization, going back to Magnanti and Wang, what Anne Campbell and Jean-François Cordeau has done. So there's differences, obviously, because this is a different system, but it's very much inspired by those work. So the trips are viewed as single commodities. These are the, you have a trip which has a number of passengers, and we view them as single commodities in this network design. We ignore the detailed routing and dispatching. We assume that the fleet of shuttles is enough to deal with the routing and dispatching quickly. We have a subsequent step, which is fleet sizing. I won't talk about it, but it's there. And obviously, in real time, we do the real-time routing and dispatching. We also assume that the buses are large enough. And once again, I will show you that this is a very reasonable assumption later on when we actually look at the resilience of the system. So this is a little bit the decision variables. And I want to talk a little bit about this because it's going to be important when we talk about mode adoption. You have decision variable for every trip, which tells you if that particular trip is using a shuttle between I and J. Location I and location J. Same thing for the bus trip and the rail trip. Do they take a particular bus leg or rail leg? And then, there are these variables that decide whether we built a rail line, whether we built a bus lines, and so on. In Atlanta, we only built, bus lines in the design. This is the model, in its more simplified forms. I will tell you a little bit about the extensions that we are making. But mostly the objective function is balancing cost and convenience. You see that you're multiplying the cost for every one of the shuttle trips, the bus trips, and then you have a fixed cost for building a bus line. You have a connectivity constraint, which makes sure that the network is connected to a large extent. We make sure that nobody can take a bus line if the line has not been built. And then we have the traditional flow conservation equations. What is interesting here is, and you probably realize this already, as soon as we fix the bus lines or the rail lines, the system the model becomes totally unimodular. And in addition to that, it can be decomposed by trips. So it's very amenable to a vendor's decomposition where you have a sub-problem associated with every one of the trips. And that's what we are doing when we are trying to solve these models. We are basically using this model. In addition to that, we use Pareto optimal vendor's cut because there is a lot of degeneracy in the subproblems. We also use cut bundling and branch and check. Now, in practice, as I told you before, people don't like to transfer. So we have also to limit the number of transfer. And if you do that, the structure of the subproblem is not totally modular anymore. But there is a beautiful transformation, and this is work by Kevin, for transforming that into a different graph, and then you restore to your modularity. And so this is very useful, and this is what we are using for Atlanta. So that gives you a sense of the planning. Let me talk a little bit about the operations here. In operations, what we do is that we do real-time optimization over a rolling horizon. So at every point in time, we are batching requests, and we optimize every 30 seconds. We optimize based on this batch request, and we assign vehicles to them, and we route the vehicles. At the same time as we are optimizing, we are batching the next generation of requests, and that will feed the next optimization. Obviously, the key point is how to optimize, and we use a column generation algorithm to do that. What it does is trying to minimize the waiting times. So that's what we do during operations. And we make sure that we serve everyone, and that obviously every vehicle is only assigned a single route. Now, there is one interesting twist here in this model, is that we are assigning a penalty for lack of service. So we may not have the time in 30 seconds to serve everyone, and therefore some particular requests may not be served. And what we do is we assign a penalty to them such that they are much more likely to be served later on. And this penalty is increasing exponentially, which allow us to guarantee that nobody is going to take very long. And obviously, we keep track of which riders have not been served in the particular period. That's really important in practice. Now, the sub-problem is a nightmare because we are minimizing waiting times. So it's a challenge. Because it's very difficult to use a traditional labeling algorithm, dynamic programming algorithm, because it's a resource constraint shortest path, but you only know the waiting time at the very end. So you cannot prune the search space nicely. Time expanded graphs are too big in this particular context. So what we use is a dedicated anytime algorithm. We use a variety of pruning techniques and generate disjoint routes for different vehicles. So this is an animation on New York City. So this is about 50,000 requests in 2 years' time. Look at these vehicles there. So these are vehicles which are idle. And the reason I'm pointing that out is that we have a relocation, a model predictive control to actually redispatch vehicles to the right place in the region. You see that these vehicles now are basically relocated to other parts of the cities. So we are minimizing waiting time, but in addition to that, we are also using machine learning and model predictive control to relocate the vehicles in the right zone inside the city. So once again, the red bar there are people waiting. The blue bars that you see there are vehicles which are idle and could be used later on. So one of the things that I told you that I would talk about is ride sharing, right? So this is the idea that people have of ride sharing. I was giving a keynote in South Africa, and I used that picture, and they say, you know, this is real. This is what people do here. So the point is that when you look in practice about these systems, as I told you before, the number of riders per vehicle is actually pretty low. It's in this particular case, it's about 1.5 for the big instances. But as I told you, in many of the systems that we have, the number of people in a shuttle are really, really low. It's most of the time it's one, and then at peak it's a little bit more. And I will show you that again later on. So let me talk about resilience and capturing mode choices now. Resilience, this is based on this very recent work that we have just finished. And we got a nice COVID-19 warning from archive when we submitted this. So what I'm going to talk about here is what happens to a transit system during a pandemic, during COVID-19 pandemic. And the first thing that has to happen for a transit system when you are in a pandemic is that you have to reduce the capacity inside the buses, inside the rail. So for social distancing, you also have to have downtime for cleaning up the various buses. You also have, and this is probably the most important part, a very significant demand reduction. The demand is really depressed, and I will give you figures in a moment. And that reduces, obviously, the fares that the transit agency is collecting. But despite these two things, it's very important for a transit to offer services. And once again, I will give you some anecdotal evidence here that this is actually affecting people tremendously. So this is what happened to MARTA, the transit agency in Atlanta. You can see the numbers here. The ridership last year and this year for various months during the pandemic. You can see, this is early pandemic, late pandemic, very substantial reduction. And this is happening both for rail and buses, very systematic, depressed demand everywhere. This is what Marta did in reaction to this, in response to this pandemic. So this is the original network that I was showing you before, and this is the essential service plan, massive reduction in the number of buses. So that's what Marta is actually running at this particular point. This is affecting people very substantially. These are two quotes which appear in the Atlanta Journal. So the first one is a person complaining that she doesn't have buses, a senior citizen, she cannot use buses anymore. She started using Lyft, but then the prices went up tremendously because of the pandemic. She feels trapped. Tom there is actually working in the city, and he has to pay about $400 now just using Uber for actually getting to work. So this is what the community is suffering from in a pandemic. And as many places have said, transit is really important for the economy, and a lot of people have said maybe micromobility is actually useful in those settings. What I'm going to show you is how an on-demand multimodal system is actually reacting during a pandemic. And I'm going to look at these real scenarios that you have seen. So you see the ridership reduction here during the early pandemic and the late pandemic. And this is what it does to the budget. Now, this is a very, you see that the reduction in budget here is reasonably small, and this is due to the cost structure of MARTA, the transit agency is in Atlanta. They have only 33% of their budget, which is actually coming from fare collection. So I will show you the result for MARTA, but then I will generalize this result later on when this share is actually a little bit higher. So what we are doing now is looking at various scenarios. So the baseline that you've seen already, early pandemic, late pandemic, and and then the strict late pandemics where we don't want any buses. So you see that the first thing that we do is reducing the shuttle fleet such that we fit in the budget and still meet the demand. You can also see that we reduce the capacity of the buses and the rail by 50% to make sure that we are implementing social distancing measures. You can also see that we only take one person per shuttle, once again for social distancing reasons. And in the late pandemic, we just remove all the buses and we have only 25% capacity for the rail. So these are the results, and they are very interesting. So the first thing that you can see is that the new design, which is all this social distancing and capacity measure, makes it still possible for us to have almost the same average trip duration. So we basically still have a very high quality in terms of service. You can see that the rail and the buses are the capacity is not used even to close to 25 or 50%. So we really can implement this social distancing measure. And you can see also that the cost, we fit very nicely inside the budget, in the reduced budget. And actually we save a lot of money here for the late pandemic and strict late pandemic. So these on-demand multimodal systems are very agile in a sense, because you can target the fleet size of the shuttles nicely to the demand. So they are much more dynamic than a traditional fixed route system. Let me show you how it looks like. So this is like the strict late pandemic case. And you see that we have only the backbone of the rail, and then you see the shuttles now, and they are still acting as feeder. It's just that they drive longer. The first and the last mile become the first couple of miles. Even longer in the south of this is where the airport is located, a little bit longer there. But still, I mean, these results are very encouraging. It means that the system can be nicely configured such that they address the depressed demand and the social distancing measure. This is what you do if you redesign the system. We didn't redesign the system here in the result that I've shown you. If you redesign the system, you can save even more. What it does to the system is removing some of the bus lines because the demand is depressed. And so that's what you see there, early pandemic, late pandemic. You remove a number of the bus lines, which are actually improving the quality of service when the demand is much higher. You save about 4 or 5%, if I remember correctly, when you do that. Now, this is interesting. This is what is happening for when you increase the fare collection part in the budget. So this is moving from 33 to 50%. This is roughly what New York City has as a fare collection. 66% is close to what San Francisco is doing. And so you can see that in general, let's say for New York City, this would be reasonable, 50% if you lose 50% of your revenue. It's a little bit more challenging when you look at what San Francisco has. There, the waiting time is a little bit higher. So if you need to actually meet the waiting time criteria that I've shown you, then you would have to increase a little bit the budget there. You can say that 8 or 9 minutes is still fine, but it's a significant increase compared to what you have in the other system. And this is explaining why. So you have a certain number of shuttles that you can afford, and you can see here that at peaks during the peak time, they are all in use at that particular point in time. And you can also see that the peak is much longer compared to Malta, which would be here, and New York City, which would be there. So there is a trade-off there, depending upon the share of the fare collection inside your revenue stream. But overall, I think these results are very positive. They tell you that these systems are actually highly resilient when you design them as an on-demand multimodal system. So let me talk about capturing mode choices now. This is the last part of the talk. And this is actually based in the fact that many of the transit agencies that we have been talking with have always told us, but this is very challenging to deploy a system like that, because if the system is too successful, I mean, you are decreasing, transit time by a factor of 2, more people are going to adopt the system. And therefore, are you designing it properly for the increased demand? Are you sizing it properly for the increased demand? And so the way you can think about this is that it's a game, right? So between the design of the system and then what people are going to do. So you design the system, you design the network, and then you propose a ride to the user and then to the riders, and then they decide if they want to adopt the system. If it's like 20% more than a direct trip with their cars, they would say, hey, yeah, this is interesting. If it's like 3 times as much, they will say, no, I don't want to do that. And so they will make a choice, and that obviously impact the design because it's going to incur more costs and potentially and more revenues. So and the design should change because of that. So that's what we are trying to do. And once again, I want to come back to the paper by Niels, Mike, and Barrett, because this is one of the topics that they actually pose as a recurrent theme in all the grand challenges that they are looking at, the integration of stakeholder behavior in transportation optimization model. And they were basically saying that, one of the things that's going to happen is that people are going to start designing this bi-level optimization model. And that's exactly what we are doing here. And I'm going to show you that in the next couple of slides. So the first thing that we are doing now is actually modeling the choice function as function of the trip convenience or inconvenience. Because the price here is fixed, it's $2.5 or something like this. And therefore, users are going to choose whether they use the transit system based on how convenient the trip is. And that means the travel time, the waiting time, and potentially the transfer. And everything is typically reduced in the transportation community to a time. Okay, how much time do they spend in the system? A transfer is like 5, corresponds to about 5 minutes of time, for instance. And then the mode choice is simply, looking at this convenience inside the system and deciding if this is sufficient compared to a direct trip. So we have a threshold function which says, hey, if this is 50% of the direct trip, I'm going to use the transit system. If it's like 3 times as much, I won't. And so we will be assuming in the experiments that we have 2 types of riders, those who are already using transit, since typically the OMTS is going to improve their transit time, they will continue using transit, and those who have a mode choice. And so they are using their current vehicles at this point, and but they can move to transit because now it's much more interesting. It's much more convenient. So the bi-level optimization is going to have a leader problem. As I told you, it's going to choose the network, and the follower for every one of the rider or every one of the trip is going to choose the best transit path. And this is, once again, this is chosen by the transit agency. The transit agency is choosing the path and offering it to the rider. And then the rider has to make a choice, and that choice happens in the leader problem. And the rider decides if she likes the transit option and then adopt transit or keeps using her vehicle. And obviously, for every rider with a mode choice, you have an additional cost. You have to pay for the shuttles, for instance, and you can potentially, and you get additional revenue, the $2.5 that I told you. So this is the leader problem, very similar to what you have seen before, but there are some interesting points here. So this is the cost of opening the bus lines or the rail lines. This is the cost of the existing users. So it's very much the same as before. But this is the people adopting transit. So what you see there is this is the decision variable whether a trip R is using transit or not. And this is the revenue, and this is the cost. So this is the connectivity constraint. This is the choice function. So based on the trip which is proposed, this particular trip is going to use transit or not. This is this choice function that we are using. And it can be arbitrarily complex. You're going to see we are not really using the internals of this. And then the follower problem is what you have seen before in the Bender's decomposition. It's essentially computing the cost. These are the flow conservation constraints and the fact that you only use a rail or bus line if it's open. This is a lexicographic problem because for computational reason, we want this to return for a particular network design. We want one particular path. And what we are doing here is minimizing the cost for transit and then maximizing the convenience for the riders. So that's what these two problems look like. Now I have to tell you how we solve this, right? And so the first thing that we do is we relax the leader problem. So we basically take this choice function there and we remove it entirely. So we design the system in such a way that the master problem can decide who is adopting the system and who is not. And then the subproblem is we are going to use two kinds of techniques. The first one are these Bender's cut, which is really what we were doing before already. You take the subproblems, do the dual, and you get this nice Bender's cut. Nothing fancy there, exactly the same as we were doing before. The new original thing is the combinatorial cuts that you need for reconciling the rider choice and the guesses that the relaxed leader problem is doing. So there can be two situations, right? So one where the rider doesn't want to adopt the transit system, but the leader wants the rider to use the transit system, and then the opposite. The leader doesn't want the rider to ride the transit system, but the rider really wants to use transit. So we have to essentially introduce these combinatorial cuts to remove this inconsistency. When you see that the rider is the choice function is telling you I'm using the system, but the leader doesn't want to, you have to exclude that. And so what these cuts are basically telling you is that if this is the design, then you have to use the transit system, or you don't use the transit system. The rider is going to use the transit system, or he's not going to use the transit system. So they are basically reasoning about whether a bus line is open, is closed, or whether a bus line is open. No, these cuts are extremely weak. So they are not very, very effective. So one of the things that we try to do is to make sure that we can strengthen them. And so this is the intuition. I'm going to give you the intuition here. So assume that a rider is actually adopting the transit system. So now if I'm adding new work in the network, then my intuition is that the transit time is going to decrease and the rider is going to continue adopting transit. So this whole part here of the cut, of the combinatorial cut, which is reasoning about the bus line which are not open, it doesn't matter if this become one, it doesn't change anything. The rider is still going to adopt the system. And therefore you can have these much, much stronger combinatorial cuts. And the intuition is obviously the same if the rider is not adopting the system. If you start removing the lines in bus lines or rail lines, the rider, the transit time is going to increase and the rider will keep using your vehicle. Okay, so you can remove the other part here, you remove this part here where the bus line are open from the cut. So this looks really great. So we were really happy, but then we realized that this intuition is actually completely wrong. I mean, not completely wrong, but somewhat wrong. And I'm going to give you the reason here. So so assume that we have a rider, starting from there, and let's say moving here. So if I'm adding a new bus line there, obviously I'm going to make it easier. And this is where the intuition that we had came from, right? And so this is what I just showed you. But there is another case which is actually really annoying. So let's assume this is a hub, but that hub was not connected to the rest of the transit system. Now, if we put a bus line there, now, since the transit system is choosing the path, what's going to happen is that it's going to allocate a shuttle to go to this particular hub and take the bus, and the overall convenience is going to degrade for the rider. And the rider may actually, at the time of the rider, the convenience of the rider is actually going to decrease. And so this is annoying. You're adding an edge to the network, but it makes the convenience of the rider increase. It increases the convenience of the rider. So what are we going to do? I think what is nice is that you can actually combine these two intuitions by not removing every edges, but removing a selected set of edges. You can actually characterize which edges are really problematic. And these are typically edges connecting the connecting apps which are inactive and which are closer to the origin and destination to where the current rider is connected. And so you can actually weaken these terms that we had before by selecting which edge you have to include and removing many of them. And that's the combinatorial cuts that we are using. So let me go over the case study now. This is the Ann Arbor Ypsilanti transit system called AAA in Michigan. This combines two cities, Ann Arbor, which is a reasonably wealthy city, and Ypsilanti, which has neighborhoods which are extremely poor. So what we're going to do is to look at different population segments. High income, you see this cross there. This is the high income population, middle income population, and then poor income, low income populations. And they will have different tolerance for using transit, obviously. And we are giving them different mode choice functions. And we are going to try to design the system such that we try to have, we model mode adoption for every one of those. So this is the experimental setting. This is a number of income rides, the rise per level of income. And we assume that for the low income, everybody is actually using the transit system. 75% of the middle income are using the transit system, and about 50% of the high income. And we put the threshold for the mode choice to 1.5 and 2.0 for the high and middle income. The system is still reasonably large. It's about 1,200 transit system. Also, these are this is about, like, say, 400,000 people here. And the average time is 7 minutes. We use the cost of the buses and the shuttles, which are typical for that particular transit system. So these are a couple of results. So this is the result for the base case, the existing transit demand. And you can see that the adoption here is increasing significantly. It's about 14, 15% there for the middle income, 20% for the high income. And here we are basically reporting the transit time for the riders adopting the system. The existing riders, are still using the system, and the ones who are not deciding to adopt the system. And what you see is that the new riders adopting the system at a very, very low transit times. Most of the high income have actually direct trips here, and much obviously the transit time is much lower than the existing system, the AAA system. These are the existing riders. Once again, we decreased the time by about a factor of 2. And the people who are not adopting the system, you can see that we are proposing a system which is better, but not that much better, not sufficiently better such that they adopt the system. So this is interesting. This is when we increase the price of the shuttle. What happens when you do that is that you tend to have many more bus lines, and that's what you see in the design. You have fewer adoption because of that. It takes more time to actually move from one point to another one, but still very healthy additional adoption. And the results, for the waiting times are reasonably the same as I've shown you before. This is when we double the ridership, even more bus lines there, very similar adoption rate. I think the results are pretty consistent. You take a little bit longer there for the existing riders, a little bit longer for the middle income people over there. This is one particular experiment here that I like very much, because what we are doing here is generalizing what I've shown you to the case where we have an entire population of low-income people who have a mode choice, but it's a different mode choice. Is whether I actually do use transit or whether I actually don't use transit at all. I don't have a personal vehicle, but the time it takes to go to the job is too high. I cannot take care of my children, for instance, or my parents. And so these people have a choice, and this is one of the things that we are trying to focus on, is can you actually give accessibility to this population segment such that they have job accessibility or healthcare accessibility. So we took the low-income population now, and we have a certain percentage of them who can adopt the system because now it's attractive enough that they can actually get a job. And so once again, you see that very high adoption for these low-income people, but there are some percentage who are not using the system. And I want to show you these kinds of rights because they are very peculiar. So most of the jobs are locating inside Ann Arbor and inside this particular location. That there are a lot of. This is a job center. These two rights here, which are not adopting the system, are very peculiar. You see this first one. This is an area where there are not that many jobs, and this is where the person lives, and so it's very difficult to actually give a very effective ride to those people. So you see this person, there's a shuttle trip there, and then a bus trip to the center of the city, and then she goes to Ypsilanti, and then there is another shuttle trip. But this is too much. It takes too much time, and therefore she decides not to adopt the system. So that gives you a sense of that. So let me, so this is when you, number of apps. If you increase the number of apps, no big surprise, you put more legs, and therefore you decrease a little bit the adoption because the system takes longer. This is the cost and performance of the system here. You can see that the price here is $2.5 per ride, and you can see that some of the systems are profitable when you double the demand, for instance, and double the number and have many apps. You are profitable. Otherwise, you're very close to to be breaking even. And even for the system where you have a very high shuttle price, you are very close to profitability. You would have to increase the price by a small amount of dollars to actually be profitable in this particular setting. This is the impact of the strengthening inequalities. You can see that they improve computational efficiency by several orders of magnitude, not only for finding optimal high quality solution, but also for reducing the optimality gaps. So they make a huge impact in giving us the ability to actually serve this, compute this network, design this network. So let me conclude now. So what I've tried to show you is that this new generation of on-demand multimodal transit system can address the first and last mile, address congestion, and also provide economy of scales. They have a business model that is sustainable, and they can really reduce transportation inequalities. They apply to many transit systems, very wide geographical region, very dense, and even a complex city like Atlanta. They are resilient under depressed demands, and they are also capable of capturing mode choices. The key technologies is a lot of optimization technology. We use almost everything. Benders, branch and cut, column generation, bi-level optimization. And we also use a real-time dial-a-ride algorithm, which is based on column generation, model predictive control, and machine learning. There are many challenges ahead. I think we need to scale some of the things to even larger network. This is where a lot of the bottlenecks are. So you have to integrate several aspects of this research together. And computationally, this is very, very intense. But that's what I wanted to tell you. And I'll be very happy to take any questions that you may have. So thank you very much for attending.
Yes, thank you, Pascal, very much. So we do have a little bit of time for questions. There's a couple in the Q&A. But I was wondering, actually, Pascal, if you could talk briefly, given that you're planning for a public organization, could you talk a little bit about equity, for example, having to serve areas equitably, if you will? Is that an issue, and how would you address that?
Yeah, so this is a very good point. So equity is one of the things that we are also trying to do. So one of the things that you can do is also design this system such that you actually increase accessibility in a particular neighborhood, in a sense. So you could actually put additional constraints to make sure that you have reasonable, time for this particular population segment. One of the things that I need to tell you is that the MARTA system is actually very equitable. So if you look at every one of the regions, the various, TAZ zones, they have essentially the same quality of service there, which is kind of remarkable in the sense that accessing a particular bus stops is the same in every one of these TAZ zones. So in a sense, by definition, since we are improving over MARTA, we are keeping this equity component that MARTA has. But you are completely right. This is one of the big issues that we are trying to do. And we're trying to make sure that the system remains equitable for every one of the region. We are not trying to improve some particular regions and some other ones. And this is a very important issue because a lot of the transit agencies have a tendency currently to focus more on the bottom lines, and therefore they remove bus lines, which are not as effective. But these on-demand shuttles are actually compensating for that because they are much cheaper, and they are much cheaper for these kinds of low density areas.
Okay, yeah, that certainly makes sense. Pascal, I apologize, I don't know this, but can you see the Q&A window?
Yeah, I can see them. The first question is whether we price the shuttle. And the key point is, I'm sorry if that was not clear, but this is a transit system. You have a fixed price for in everything that I've shown you. We assume a fixed price for the tickets. So in Atlanta, it's about 2.5. I think in Ypsilanti, it's 2.5 or $3 or something like that. So we assume that this is a fixed price. The riders don't pay for the shuttle. Now, this may not be completely fair and so on. So we are looking at pricing right now. Beste and I'm going to look at that as well, where you could actually price people differently based on the cost that they have. This is an interesting question, but everything that we have done so far is a fixed price. Vedad asked if we can share the slide of the presentation. Yes. So carbon emission. Yes. So carbon emission is an interesting topic, right? So Zenep is asking, how can we actually measure the emission level of a system like this compared to personal vehicles or a transit system? So what I can tell you is that compared to the vehicles, obviously, we have way fewer miles, and therefore we save a lot in carbon emission to the current way of commuting, the current way people are commuting in a city like Atlanta. But I think the real potential here is that we own the fleet. And therefore, we can actually use only electrical vehicles for actually operating this transit system. And this is, for me, a big advantage. And Ramon and I and others in the group are actually working in actually quantifying exactly how you can charge these vehicles as effectively as possible. So this is research that we are doing, and we'll report these results soon, hopefully. So my point here is that the hope is that if you team this with renewable energy and only use electrical vehicle, essentially this transportation system will have zero emission. And that's what I'm really excited about. The next question is about the number of shuttle, which is significant. Yeah, so we'll provide those numbers when we do the. So that's a question from Gulnas. I'm probably destroying that first name, but he or she is asking whether we can provide a result for CO2 emission, and we will do that. We have done that in different settings, but I can point you to some papers that we have written linked on that, and we'll report them when we do the electrification paper. That's a good question as well. And yeah, so Anne is asking about the ridership choice and what is the mode function. So the mode function that we have right now is the time you spend in a vehicle, the time you spend waiting, and then you could include transfer, which is essentially what people care about. And you can reduce that to one number. That's what they typically do in the transportation industry, right? So there are different ways for waiting. People don't like to wait. They prefer a longer time in a vehicle compared to waiting. And then the transfer, people really dislike transfer. So you can capture that in the function. Now, if we start pricing this is going to be more complex. So we would have to actually try to find once again how you can actually merge time and price. Once again, if you look at what they are doing in the model for mode choices and so on in the transportation community, they also reduce everything to price. So time as a cost, and they model that. So we could actually do that as well. Now, this is a good question for Anne, because it allows me to actually point to something very important, is the fact that we are actually, the choice function is a black box for us. We don't care what it is. It can be as complex as you want. Because the only thing that we are doing is using these valid inequalities for actually reconciling the choice of the leader and the choice of the rider. And therefore, it's not only these combinatorial cuts that are being used. We don't use the internals of the cost structure. So this is a strong point of the methodology here. Somebody is asking, well, this is like a lot of questions here. So what software is used for creating the visualization? So we use a variety of software, but all the visualization that you have seen today are done by Sam Baskin, one of the undergraduate students working in the group, they are using Folium and some dedicated software that we've written for automating this, such that we can basically give a trace of what the system do and automatically generate the animation. Yeah, so very good question for Iman, which is saying the current transit system is not door-to-door, but the new system is. How do you compare the cost? So the cost, I think the cost that we are giving when we are saying that we are actually reducing cost and things like this is actually very conservative, because when we look at the rider of the rail in Atlanta, they have to come to the rail, and we don't need what we do is essentially door to door, right? So so we don't know where these people are coming from if they are using the rail. They may drive there or they may bike there and so on. So I think but we don't have that data. This is data which is much more difficult to get. So we only have the OD pairs of, where people are, which bus stops they are taking and which or which rail station they are boarding and alighting. So I think one of the things that we are doing in the group, and this is also based on this, what the transportation community is doing, is taking these OD pairs and then looking at point of interest and residence and actually distributing them as best as we can inside the TAZ zone. That's what we are doing as well, such that we capture these costs in a more precise fashion. And the final question that I have is, how do you estimate the demand? The way we estimate the demand is simply because we have all the OD pairs from Marta. So we have exactly all the transaction. Every time somebody takes a bus or goes to a rail, we know that they are doing that. And therefore, that tells us what is the ridership in the transit system. So I think I covered all the questions. So thank you very much for all of them. These were really good questions.
Pascal, thank you so much for your time. I really appreciate it. And I think clearly we all greatly enjoyed this. I know I did, if nothing else, or no one else. So I think that's the end of our session. Have a wonderful day.
Thank you very much. Bye-bye.